Hello, today we're going to cover section 1.2, Applications of Linear Equations. In this section, we're going to first start by trying to identify each of the different word problems. Here are some of the different types that we're going to look over today. Some I refer to as just translating problems, where you're translating the English words into mathematical statements, equations. We're going to be looking at problems involving decimals, money, mixture, and interest problems in that category. We'll be looking at distance, rate, and time problems using the distance formula. And we'll be looking at problems that are referred to as work problems, where you have two people or two machines working together to complete one job. Our first example, problem number 9 from your electronic textbook, I refer to as a translate problem. As you read through the statement, you realize what we're doing is translating the English into mathematical symbols. So we start off, Steve and Tom sold 125 tickets. So that's a total number that they sold. They then go on to describe Steve sold one more than twice as many as Tom. So notice here when I represent Steve, I represent it as one more, so addition, twice as many as Tom. Since we don't know how many Tom sold, we label him X, and Steve would be 2X plus 1. Again, the one more than twice. How many raffle tickets did they each sell? Well, we have the total of 121, so what we do is we put this together in an equation. The amount that Tom sold plus Steve's equals the 121. We then solve for X. Coming up with X equal 40, we realize that 40 represented Tom. So we can say Tom sold 40 tickets. Steve, remember, sold one more than twice that. So 2 times 40 plus 1 would give us 81 tickets for Steve. This next example I relate to a translating problem once again, but this one involves money, so we're going to have decimal points involved. As you take a look at the problem, it says Emily had $18.75. Again, that sounds like a total. Reading on, it consisted of dimes, quarters, and silver dollars. So I labeled those things here on the side. She has 7 times as many dimes as silver dollars. We don't know either one, but notice how they're describing the dimes in terms of the silver dollars. She has 6 more quarters than dimes. Once again, we don't know either one, but they're describing the quarters in terms of the dimes. So let's go back to the first part. 7 times as many dimes as silver dollars. So since they're describing the dimes in terms of silver dollars, we label the silver dollars first as X. The dimes is 7 times as many, so we're going to label that 7X. Then reading on, we have 6 more quarters than dimes. Well, if 7X is our dimes, 6 more would be adding 6. So 7X plus 6. These 3 should total money she had. But what we must realize is that this is just representing the number of dimes. Each dime has a value of 10 cents, which if you write that as a decimal, 0.1 or 0.10. Same thing. Each quarter has a value of 25 cents, and we write that as 0.25. Each silver dollar has the value of 100 cents, or 1 whole dollar. So we multiply the amount of each coin times the value of it. Set it equal to $18.75. We can then work with the decimals, or we can choose to get rid of them. We can get rid of them by multiplying by the necessary power of 10. Since I have 1 decimal place here, 2 here, and 2 here, it appears that 2 decimal places is the most amount that we have in this problem. So we're going to need to multiply everything by 100 so that it will move the decimal point 2 places to the right, therefore removing decimals from the problem. So when we multiply everything in the problem by 100, we end up with this equation here. Solving for X, we end up with X equal to 5. Looking back at what we labeled over here, which is always good so that we can remember what each thing stands for, the X was representing the silver dollars. So we have 5 silver dollars. That means we have 7 times as many dimes. So 7 times 5, 35 dimes. And remember, we have 6 more in the quarter category. So 7 times 5 plus 6, 41 quarters. Our next example I refer to as a mixture problem. In these problems, you'll be mixing different types of food or sometimes chemicals, but you're mixing things together to get a final product. So I like to use a chart to set these problems up once I recognize that it's a mixture problem. So I read the problem to see what we're mixing. In this case, we have a gourmet brand of coffee and then a cheaper brand that we're mixing together to create a new blend. I then read the problem over to find the details. Apparently it's going to be $9 a pound for the gourmet, $5 for the cheaper brand, and we hope to sell the new blend for $6.50 a pound. As you read through the problem again, you realize that in the end we want a total of 30 pounds of coffee. So the 30 goes down here at the bottom. We always put what we're trying to get at the bottom of the chart. How do we then represent how much of the other types of coffee? Well, in math, it's very common for them to give you a total value and then have you separate it into groups, 2 groups. Since we don't know exactly how much is in each group, we can label one of them X and then label the other the total minus X. In other words, whatever's left over after you put X amount on this side, you have the total minus X left for the other side. So that's how we labeled this. X for one of them, and then the total, which was 30 pounds, minus whatever we put here, is what is going to be in this category. Now, since they're charging $9 for every pound, and we have X amount of pounds, we multiply to represent the final value of the gourmet coffee. Multiply straight across. Same thing for the cheaper brand, and same thing for the new blend. The nice thing about the chart is it helps you organize all of the details, and then your final equation will come from the final column. We're going to take the gourmet coffee, 9X, add it to the cheaper brand, and it should equal the new blend. So what we're trying to do is take these two and mix them together in such a way that we can now sell them at this price and still make as much as we would have made selling them separately. So now solving for X, we end up with 11.25. Looking back at the chart, X was representing the amount of gourmet coffee. So 11.25 pounds of gourmet would need to be mixed with 30 minus 11.25, 30 minus X, which would be 18.75 pounds of the cheaper brand. This next example, as you read through, you realize is an investment problem involving interest. The formula for interest is interest equals principal times rate times time. Principal is the amount of money that you're investing. Rate is the percentage of money that they're giving you for the investment, and time is usually in years. If they do not specify a number of years, it's assumed to be 1 year. This person had $28,000 to invest in 2 investments. One of them paid 4% and the other 5%. How much would she have to invest in each one if she wanted the total interest to be $1,320? So again, I like to use a chart for the interest problems to organize the information, and then my equation again will come from the final column. So here we take a look at the top labeling here. We have principal, rate, time equal the final interest. I labeled this first and second account because they just said 2 investments. Sometimes they will specify bonds versus CDs. All right, so principal, how much money should she put in each one? That's the unknown. What we do know is that she has a total of $28,000 to invest. So once again, like the problem above, we have a total that has been separated into 2 areas. We let X be the first amount, and we can let the total minus X be the second amount. So 28,000 minus X is represented here. The rate for each investment, one is 4%, which we need to convert to a decimal, and we do that by dividing the percentage by 100, which moves the decimal point 2 places to the left. So that's how we got the 0.04. The other is 5%. So again, dividing by 100, we get 0.05. The time is 1 year. And so now to get interest, remember you multiply these three together. So multiplying across, this is what we have to represent the interest for one account. Multiplying across, this is the interest for the other account. And this is the total interest that she hopes to get from both investments. So the equation comes from the final column. We add the first interest plus the second account's interest equal the total. Once again, you can work with the decimals or you could get rid of them. In this example, I chose to work with them to show you that it can be done this way as well. So distributing the 0.05, combining like terms, and solving for X, we end up with 8,000. Well, X was the principal for the first account, the 4% rate. So our final answer says that we should invest 8,000 in the first account paying 4%, and then 28,000 minus 8,000 for the second account, which would be 20,000 that we would put in the second account earning 5%. This next example is a distance problem. The formula for distance is rate times time equals distance. The rate here would be the speed. Reading the problem, you will usually recognize that there are either two modes of transportation, or sometimes it's just going and returning on a trip. In this example, it's going and returning. So as we read through, we realize that the pigeon is flying with a tailwind of 10 miles per hour. So what's happening here is the pigeon is flying at a certain speed, but the wind is behind him 10 miles. So it's going to increase his speed when he is going, X plus 10. On the return trip, the wind is going to be pushing against him, so that is going to decrease his speed by 10. Now notice they give the time here in minutes, but they gave the speed in miles per hour. So we need to have the same type of measurement for the time. So we're going to convert the minutes to hours. Well, remember there's 60 minutes in every hour. So 15 divided by 60 would equal 1/4 of an hour. 15 minutes being 1/4 of an hour. The other time returning was 30 minutes. So 30 divided by 60, 1/2 of an hour. Now that we have the rate and the time, we're going to multiply across and find the distance is 1/4 times this going. It's 1/2 times this returning. Notice in this particular problem, they did not give us any other information. There's no total like we had in our other examples. So when that happens, you need to ask yourself, are these two supposed to equal each other? Well, think about it. If you begin at a certain location, fly somewhere, then turn around and return back to where you started, what can you tell me about the distance going and returning? It's the same. So we set them equal to each other. Notice our equation is still coming from the final column, but this time we set them equal to each other. We now solve for X by getting rid of the fraction, multiplying both sides by the LCD, and we've come up with X being 30. Well, that represented the speed of the pigeon in still air. Our final example is what we refer to as a work example. Here we have two people working together to complete a job. I like to set these up by creating two fractions, adding them together equal to one job complete. Each fraction represents the effort that each person is putting into the job. So you put the time they work together on top, one person's individual rate on the bottom, and the other individual rate on the other bottom of the fraction. So here we have Tommy and Huck. Apparently Tommy's rate is 5 hours. He could get the job done by himself. Huck, we do not know his rate. That is what we're looking for, so we label it X. If they work together, they could get the job done in 1 hour, so time together is 1. We add Tommy's effort plus Huck's effort, and it should equal 1 job done. This is our equation to solve. Since it has fractions, we find the LCD. We multiply everything by the LCD, removing the fractions, and solving, we end up with x is equal to 5/4 hours, or 1 1/4 hours for Huck to get the job done by himself.